So we were having a good old discussion of mobile phases, and the mobile phases that we were talking about was bicarbonate and carbonate. So what we want to do is that we want to follow through with us, right? We want to give you a little bit more detail about a bicarbonate carbonate mix. And the very first thing that you should realize is that because this is a very common mobile phase, bicarbonate and bicarbonate, you have to start gravitating yourself toward the computer screen and the detection signal that's coming from your instrument. The bicarbonate carbonate, because these do have ions, they do generate a little bit of signal. No matter what you do with them, they're going to generate a little bit of signal. And that means a little bit of conductivity is going to show up on your software and your instrument. So you will never see a zero conductivity that happens because of it. What kind of conductivity range should you be looking at? And this should always be 10 to 20, what we call microsiemens, S-E-I-M-E-N-S, microsiemens per centimeter. Some people will write it microsiemens over centimeter. That means the same thing. So 10 to 20 is the range that you should always see on the software or from your instrument detection. As long as you've made your mobile phase the proper way, and that mobile phase is flushing through the machine and no samples going through the machine, this should be your conductivity on the instrument, 10 to 20. And ours normally is in that range. It normally is in between 13 to 14 in terms of conductivity value. If you're pumping mobile phase through, and it is a bicarbonate-carbonate mix, and you have no sample coming through, it's just mobile phase, and you start seeing conductivity that goes up to like 175 or 250, then we know that there's a problem. That mobile phase has been prepared incorrectly, and there's no sense in going any further with your IC analysis until you lower that conductivity value down. It has to go down. So do not waste your time running samples on conductivity that's reading 170 or 180 or 200 microsiemens. It's not going to work out for you on the anion side. All right. So again, I'm going to put in all capital letters here on anions, because they are the ones that use the bicarbonate-carbonate mix, which is the most common mobile phase that will give you that 10 to 20. So every day that happens, if people are making mobile phase in the lab and they load that mobile phase up on the equipment, I'm going to quickly look at the conductivity value of the detector after I'm running that mobile phase through for about 30 minutes. I'm going to let the mobile phase kind of travel through the instrument. I'm going to allow it to travel through that column. I'm going to allow it to go through the suppressor unit, and then I'm going to allow it to go through the detector. That takes about 30 minutes in total. I'm going to give it some time. But after 30 minutes, if my conductivity is not 10 to 20, then I'm fighting a losing battle, and I just need to not run any sample at all until I figure out what has happened to my mobile phase. Very often, what that requires is for you to get rid of the mobile phase that was made, and you need to remake the mobile phase and then place it back into the instrument, give it another flush for 30 minutes, and hopefully that begins to go down. Another reason that your conductivity might go up is due to suppressor problems. And the suppressor problems we need to talk about in a different section, because this could also lead to very high conductivity values on the anion side. So again, we'll wait off on that, but right now, if your conductivity is not expected 10 to 20 and you're getting a higher number, your solution at this moment, your only solution, is to dump the mobile phase out, remake it, and put it back on. All right? The reason that we get a slight conductivity value, a 10 to 20. That means that this bicarbonate-carbonate will eventually go through the suppressor. And what happens here is that the suppressor will convert this to carbonic acid, H2CO3, or HCO3. And sometimes these things can escape through, and we get a slight charge due to that in the conductivity meter. Not all of it is going to convert, but we do get carbonic acid that happens really after the suppressor system is engaged. So a little bit of H plus, a little bit of HCO3 minus, a little bit of H2CO3, but that slight negative HCO3 is the culprit, and that's what begins to do it. The acetic acid addition, sometimes we add acetic acid to the mobile phase mix, and acetic acid comboing with carbonate bicarbonate is not a big deal. It's not a big problem. The acetic acid is HCH3COO. I've just written it a different way. You might have seen it CH3COOH, and if so, that's fine too. But what happens here is that this acid will break apart, and we will have a acetate that carries with it a negative charge. This allows separation to happen a little bit better. We've thrown in another ion. This ion is a little bit bigger compared to the bicarbonate ion, and maybe I can get separation to happen a little bit better on my chromatogram. So it just aids in the separation. Sometimes it's needed, sometimes it's not. It really just depends on the standard operating procedure that you're following. So just follow the method, and if it does say add acetic acid, not a big issue at all. It's just creating a little more ion for you in the mobile phase to help improve your resolution and to separate these things maybe a little bit better. The acetic acid disassociates. The pKa here for acetic acid, I think, is around 4.76. Now, I could be wrong. I'm not looking at a chart in front of me. But 4.76 pH is really where acetic acid begins to spit off the proton. In these mobile phases, acetic acid is only about 20% disassociated. The other 80%, it kind of stays together, right? This acetic acid, remember, is a weak acid, meaning that it doesn't give off all the proton all the time. It's going to hold on to quite a bit of it, and it holds on here about 80% of the time. 20%. We get this little acetate that's swimming around in solution that can help improve my resolution, that can help improve my retention times and the separation of the components. So that's why sometimes we add it, sometimes we don't. Again, that just really depends on the method. So just do what the method tells you and you'll be okay. All right? So that's really all that I want to say about the bicarbonate-carbonate mix at this time. So the number one common anion mobile phase is your bicarb-carb. You make it. It could have acetic acid, it might not. If it does or if it doesn't, it doesn't really matter. You're going to get the same signal that's coming from your detector, and that should be about 10 to 20 microsiemens on the software. If it is not 10 to 20, you know the mobile phase has changed, the mobile phase is different, someone did not prepare it the proper way, and you're going to have to dump it, and you're going to have to remake it. All right? Okay, now the next mobile phase that's up to bat, this is another common anion mobile phase, and this mobile phase is going to be just a hydroxide based. Typically, NaOH or KOH is used for this alkali mobile phase that goes onto the IC system. All right? The good thing about sodium hydroxide and potassium hydroxide, when it goes through the suppressor unit, remember how we said that the bicarbon makes carbonic acid sometimes? The suppressor unit, when these go through, it's actually going to produce water. And this water does not carry with it any conductivity at all because it will be pure water. We're using deionized water in the beginning. It has a little bit of NaOH or KOH in there. It goes through the suppressor does its job, and it spits out water as a product. And that water is pure water, HOH, and that does not carry any conductivity at all. What that means is that these are great. NaOH and KOH mobile phases are wonderful if you do not want any background noise. Very often the background noise here, you can't even really detect it. It is so low, and this allows us to go very, very low in concentration units. So if we do want to see something on the screen and on the chromatogram that has a very low concentration in terms of part per million maybe, then NaOH and KOH will allow us to see that a little bit better. The baseline is not as noisy. It is pretty much a flat line all the way through, which means that we should get something close to 0 microsiemens per centimeter here as far as the conductivity goes. All right. The problem here, though, is that NaOH and KOH, they're really, K is a positive, OH is a minus, and there's no variation here. So these do not work out very well for very complex mixtures. You know, if I've got a lot of things that maybe have that fluoride or chloride both carrying a -1, and maybe a lot of other things that are carrying a -1, the NaOH and the KOH is going to have a hard time separating those perfectly from each other. And that's because, unlike the bicarb-carb, this is just really giving me one version of an anion with one charge and a cation with one charge. There's not a combo unit that's coming along here. In addition to this, you got to kind of worry about sodium hydroxide and potassium hydroxide sometimes, and that's because some of the columns, if you are not very careful, can be damaged by your sodium hydroxide and your potassium hydroxide mobile phase. So you have to make sure that you pick out the proper column. That proper column has to be suitable for an alkali mobile phase. If not, then the stationary phase in that column can start to degrade and break apart, and that stationary phase is now ruined, and you will not get separation no matter what you do from that point until you replace the column with something that's a little more proper. Sodium hydroxide and potassium hydroxide also has a problem in the mobile phase bottle. So if I've got NaOH here that is getting used and pumped through this bottle, what you tend to see is that this alkali will actually leach the silica from the glass that you are putting it in. And that is going to make a silicate. And that silicate is going to be picked up by the detector. It ruins your columns, it ruins the pump, it gets picked up by the detector, you get higher background noise. There's tons of things that happen with the silicate anion that gets leached out of your glassware containers up at the top of the instrument. So for that reason, you kind of want to use plastic instead. And you also want to make fresh mobile phase each and every single day. Do not allow your mobile phase to sit into that jug overnight. When you come in into the morning, you want to make a fresh batch, put that batch up on the machine, let it go through some equilibria for about 30 minutes, and then you're ready to run your samples on the ion chromatograph. All right, so recommended storage here is in plastic bottles, and that's because in the glass, it begins to leach silica out, and that silicate is going to be picked up in the detection unit. So this base is great for low concentrations, but you just got to kind of be aware of the problems that the NaOH or the KOH can have onto the storage of the mobile phase on the machine. There's a couple of companies that are out there now, Metrum is also one of them, that have kind of modified this whole technique because they know that that's a problem. And what they're doing now is that they have a bottle, and you just literally put DI water into the bottle. And this pump will suck water out of the mobile phase jug, and it will send it through basically a chamber that has a KOH or NaOH membrane. And then after it passes through that membrane, you will then have maybe NaOH mobile phase or KOH mobile phase that is getting automatically prepared for you. What that has done for an analyst in the laboratory is that you don't have to worry too much about the storage capability of your mobile phases anymore. This KOH or NaOH is getting used as it's needed, so the water's getting sucked up from the bottle, and then it's eventually going through this membrane area where it's leaching and mixing some NaOH or KOH with it, and then it eventually goes into your column. So it is a more automated mobile phase prep for you, and some people have loved it because of it. No longer do they have to worry about all of these complications that come from are NaOH or KOH mobile phase. Right? So that's where I'm going to stop this video. In the next video, we're going to continue on with the sodium or potassium hydroxide, and we're going to talk more about some of the problems that I might need to watch out for if I use this mobile phase in the lab, and how to fix those problems from happening or prevent those problems from happening.